So,
Oh, thanks for the chance to speak. And I think this can serve as an application of this Frank's Pi1 diffeomorphisms terms in global analysis, which Professor Boylan is going to speak about. Right? This is also a direct generalization of Frank's Magnus classification. So I hope it's not too elementary. So the definition, I'll first define this system that I studied. So let's define that we need the fiber bundle I guess I assume C1 because I only need the topology.
Right.
Oh, okay. Let me be a fiber bundle. I assume C1 and have. Okay. So as we call apparently Fibrewise. And also if okay, let's also assume C1 because I don't study measures or whatever. So C1. So if there exists metric the invariant splittings what's a tangent bond of the fiber bundle into vertical and horizontal. Vertical is tangent to the fiber, horizontal is tangent to the base, right? And vertical bundles within ES plus mu and constants b greater than 0, lambda 0, 1, and n greater than 0. If BS is equals, then we have the equal A. This is here. So note that if P is a point, then this reduces to the usual Anosov details.
maybe try a different piece of chalk.
Okay. Maybe. Okay, I guess example. Okay, but let's take another. Given us want to take a different matrix probably. Right, this is different from that math. So fibrewise, then I can give a fibrewise and also diffeomorphism. So that F say to anything, right? B can be anything. At F field, D field. That's what the product. That's a trivial. So this is like the trivial example. So
Fibrewise and also and also.
it just have a base. So this okay. Let me.
I guess it comes from TA. What is TA? The tangent to the fibers, I guess. Yes, that is tangent to the fibres.
No, it's tangent to the entire. So this one is tangent to the fact.
Splitting, this is splitting of the tangent space. It's like skew from it. You're acting by F on the base and the Anosov in the bundle.
Yeah, it can have a map. It just have immerse on it. So let me say this fibre-preserving. So I'll give more examples later. So this is a trivial example, example one, right? And let me state the theorem. Thanks. Right, the classic one. So let's add the Anosov diffeom. Let me just say new manifolds. Manifolds are finally covered. So manifold. Then F, then there is a right explicitly H. Okay, homotopic identity, such and hyperbolic. I'll define this self-contained, right? Hyperbolic new manifold. Automorphism. Say such that this is my it's a, so this is what people usually call conjugates. So let me say what it means by hyperbolic. Automorphism. But just in our Anosov case, right? We have Anosov details that of new manifold. This is a new manifold. It's and it's a simply connected. Potent leader. Gamma is just a fundamental group here for lattice, co-compact lattice. This so we get that gamma automorphism from gamma to gamma, right? And I think I should call it all slender or alpha. I don't know where to put probably here. That this uniquely extends to G an automorphism. And I say it's hyperbolic if this at the identity doesn't have any eigenvalue. On the unit circle. So I guess if it's a torus, then it's the same as this. But if it's a new manifold, I still want some map on the vector space to say eigenvalues.
So DG is the derivative or action on the knowledge, CG.
Yeah, on the algebra, yeah, it's a derivative.
Derivative.
Yeah. I think.
It's off in the circle everywhere.
Uh-huh. Right. Let's see. So I have a remark. This is a different question, right? But remark, these are so these examples in the classification, the algebraic examples, so-called, actually are all the known examples. So question, I don't know whom to refer to, but yes, refers to the famous people. So that's all Anosov, that's every. So Diffeomorphism. I don't think it's the worst problem. You up to my color.
Language, so they only on infranumeric
Yeah, that they're finally covered by.
language.
Yeah. So. Yeah, let me give my definition of principal bundle now. So I think I just need to, there are many equivalent definitions I just know. So I think I just need E to be metric space. And to admit, say, let me just define principal torus bundle for my purpose. TD bundle. For my purpose, so E is a metric space and admits a so continuous and so per to the action. So it has torus fibres. Now I can give more examples. So example number 2, I guess if I have the Newman hyperbolic diffeomorphism of a new manifold. Say, so this is n modulo gamma, right? So then I can take the center of n, which is a torus, in the sense of maximum abundance. So then center. And then I consider this. This is a torus state. This is TD. Then this one okay, if I have an automorphism of an Newton Lie group, it's preserved center. So G preserves this torus. It's fiber preserving, so this is an example of Fibrewise. So example number 3, I guess one of the reasons that I'm studying this kind of examples is theorem. This is Bololev on Panida. Rodriguez Hurst. They construct different kind of examples of partially hyperbolic systems, which are this kind of diffeomorphisms. So there exists a class of partially hyperbolic which are Anosov Torus principal Torus bundle at least of dimension, at least of dimension 2 over K3 surface. Torus bundles over K3 surface. Yeah. Okay, they said it's new in terms of before this, there are only trivial examples, kind of one map of Anosov flows and these normally hyperbolic systems, which, okay, these examples are hyperbolic along the fibres, right? So normally hyperbolic systems are hyperbolic along the base. I guess that's a little bit confusing us sometimes.
K3 surface is complex surface real dimension. But your bundle fibers are the same dimension?
Dimension 2, at least dimension 2. They can have different dimensions.
Different dimensions.
Yeah. So for me, it's just 4-dimensional torus and with the involution and 16 singularities attached complex projective plane. Right. If you want to look for this, it's 15. Okay, I can state. On the term, actually 2 years ago, if I have every Fibrewise and also DPO only principal Torus bundle is topologically conjugate to an A map. I'll define A map. So A map is mapped, say G is on the principal torus bundle, and E is a point. T is something in the group. Then G, E acting on the right equals G 18. It has a linear part. Note that this can depend on the point. It doesn't. Okay. The way to find this A map is you try to tighten up this map to make it this part to make it only depends on the point on the base. So you have something like an alpha one in the fibers, but that's later steps. So these are A maps.
Choose from the bundle to the bundle.
Yeah, yeah.
Here is the fiber.
Mhm.
Then you're performing this, where
Yeah, this is also
A is linear.
A is yeah, A is in G easy.
capital G moves can move the base point and the fiber point.
Yeah.
But then after you do that, you hit the fiber with the lane.
Mhm. So, yeah, I probably want to say, yeah, so this conjugates the fibers over the identity. So G, the map that we're looking for is just the same in the base. You just need to do things in the fibers. So this conjugates the this fibers over the identity of B of the base and reduces identity. We probably put this way on H1 CD.
Does A depend on the point, the base, or not? And it just
It doesn't depend on the point of the base. Yeah.
one linear hyperbolic.
Yeah, hyperbolic. So I'll go through the proofs. I said it's a direct generalization of Frank's Manning. So and I guess it's also good to demonstrate Frank's Manning, right, for grad students. So I'll just say steps of Frank's Manning and how it pushes through. But as for me, the first step is also like find the linear model, right? So for one remark on Frank's Manning. So for them, of course, this one is naturally the okay, let me probably just have about the hashtag I want. So for me, since the bundle is compact, I can find recurrent point in the base. For example, B, I come back. Let's say a very large power of F, a large, and then it's locally trivialized, right? So I can look at two fibers, I project. So then the projection of the restriction of the Fibrewise Anosov to the fibers at B, I project to the same fiber, it's not so. So the thing is that my Fibrewise Anosov can allow some, for example, rotations of the stable and unstable in the fiber, right? So we need to argue that this is Anosov, but it's a standard argument. Or if you don't like this, I think another thing that you can do, let's see, where is it? Yeah, another thing that you can try to do is use, for example, here, closing lemma in the base that you close, then you get a periodic point, and then this one is obviously Anosov, and you just need to show, you need to show that there is a map that covers this, right? So this one is in the base, you perturb in the base, then you need to get a map in the bundle that covers this. Then you say that it's Anosov, then this one gives us the matrix by transplanting. This one gives us a transplanting. One gives us an A hyperbolic.
If you have a fixed point on the base, I believe that the fiber, the dynamics of the fiber is also. But why do you have a closing lemma on the base?
That's pure closing, I think. So something like if you have compact space, then you can have like
You would assume some recurrence.
yeah. And then you can,
Transitive clear.
No. But you always have at least a one point. Okay. And then you.
She is just one.
Yes. Yes, for fixing one of the action on the origin of the fiber, to know that this action is hyperbolic. So it's more clear if you close further orbit, so you know now that you have an hyperbolic automorphism fiber, then you get.
yeah, I guess one thing that I want to say is why this one, okay, it's by compactness, this one is the same for all the fibers, right? It's just extending by the nearby fibers are the maps in the nearby fibers are homotopy. So and by compact, usually compactness, then you can extend.
Local triviality. Local triviality.
Yeah, right. Next step is I have this matrix A, I want to construct the A map. So how to glue this matrices, right? Construct A map. This is since it's not a vector bundle, you can't easily glue things by version of unity or whatsoever. But this one, it's actually my favorite in this thing, but a little algebraic topology exercise. So you get an A map safety. And G is homotopy. Yeah, I forgot, but I actually want to say something about transplanting, why this is hyperbolic, right? So you have two ways of counting periodic points. Okay, probably right somewhere. That's where that's at. But the two ways of counting periodic points. One is from the Leftis. Leftis number, and second from coding. Then you assume there is an eigenvalue on the unit circle and compute the exponential growth rate of the periodic points, then this one gives you contradiction. So that's why you don't have eigenvalues on the unit circle. That's a short remark. Then I continue with step 2, step 3. Step 3 is to construct semi-conjugates. This is friends. Since I have nice fiber preserving maps, I can actually directly use it as a Frank's Taiwan diffeomorphism. And then from the global analysis. It's the contract mapping theorem or something like that. You'll see Professor Whalen's lecture at least.
Periodic from the current perturb mapping.
Yeah, you can.
You can perturb.
Yeah,
Something.
yeah, I think the idea of pure closing is that you can find a very close C1 close or C whatever
So
close.
you assume you can perturb.
Yeah, you perturb and find.
Typical.
Yeah. I don't know what typical means though.
If you prove something by first perturbation of your map in the base, you should prove something generic.
I didn't prove that.
No, it was in the base.
Okay, you mean how do you find a map that covers the perturbation?
Which he's worried about, you have to apply Pew, you have to perturb the map, now you have a new map. You have to connect it to the map.
Yeah, it's close in the fiber, so it's homotopically the same.
You
Right?
don't change the action in the fiber homology, because there is more perturbation. So if you prove that after perturbation, it was hyperbolic, so it was hyperbolic before perturbation. But it's not leading to perturb. Yeah.
So hyperbolicity is the actual.
Yes,
It's just stable. On top of it.
Yes. Okay, then number 4. Yeah. Number 4. So this is seems to be so global product structure. For me, global product structure means it's enough for me to lift along the orbit. So I'm lifting, say I just lift along this. So I don't consider like the lift of the bundle or anything. So structure, that means for diffeomorphism on one diffeomorphism on the manifold, it means stable and unstable intersect maybe once. Universal cover. Because this, right? You and say if I have points, then intersect only once. And yeah, remark is and also from new manifolds has this, right? And also have this. And another thing is from the window, like I think this thing is an important property hammer in the if and another has polynomial global product structures, then this manifold is a new manifold. Implies new manifold. So I would say this means global product structure plus Yes. Okay, say F, X, Y. This one. X. Plus. Yes. Less than a polynomial of Px. So this plus this is less than a polynomial of this. So that implies the manifold is a new manifold. Relies on the polynomial growth theorem of Gromov, I think. So, then last step, right? Already last step. The last step is to show injectivity. Injectivity from here. So say I assume these are in the universal cover, since the map is homotopic to the identity, it's enough to show in the universal cover. So I have you say just U1. It's not equal to U2, but H. Say this is the semi-conjugacy that we constructed. Now assume. Right. Then let's say E2. And I can find the unique intersection between, say, this is unstable, this is stable. It's E3. But under H, it maps to the same point. Okay, what? H is proper, a proper map, which means maps inverse image of the compact set is compact. The H shall be compact. Now, another nice property of the global Fourier structure is saying, say if I take 2 points on the leaf, it's uniformly bounded about for a fixed compact set, and you consider that transformation of it. Right? This is these things bounded about a constant. Now I'm starting to iterate. Let me do that. 1, 3, right? E1, E3 is on the unstable leaf, this goes to infinity, so it's
You're in the universal cover of the fiber or the whole metal?
Oh, fiber. I just consider like these ones, I only consider along orbit.
H is the Frank semi-conjugacy.
Yeah. Yeah, I think that's the average, but so I guess further questions and probably last remark, in case anybody asks, I didn't consider new manifold fibers. You probably question new manifold fibers. I didn't consider because I lack motivation of these. Because I didn't see interesting examples, right? But I guess personally, since I'm more interested in like groups acting on manifolds, and they usually do the suspension of group actions, and they have like group in the base and manifold and fibers. It's probably interesting to study like such Fibrewise and Anosov maps. Okay, I guess I'll just end here.
Perhaps you can ask where it's fairly obvious, but you get structural stability on the theorem.
Structural stability. I mean, okay, you mean the
Right, so you proved the theorem about conjugacy. But you didn't prove anything about small C1, C.
No. This one is, I now feel this one is appropriate, but this one means global structural stability. It's not the local one. So it's not the real structural stability for Anosov detail. For C1 perturbation. I'm sorry about this. I did make this title. Is that okay? So this one means the global one. I didn't mean the local one. So the C1 perturbation.
Hyperbolicity, to start from hyperbolic, then conjugate is close to not. Then it's not
Question,
uniqueness.
but you're only allowing perturbations.
So what's your question? Again?
Well, no, I just wondered what you meant by structural stability.
Right, you can it's conjugate to the linear model.
Yeah.
If you make a perturbation keeping the same basis,
Yes,
you will not change the linear model, so they are both conjugated.
But
So
we start from
Yeah.
original ones.
But you have one which acts the hyperbolicity in the fiber is an open condition.
But she needs to assume it, and she assumed it.
For the starting point, yes.
But if she didn't assume it, it would also be correct, the true, but the conjugate would be semi-correct.
Other questions?
Sorry, just to sum up this discussion, if two nearby Fibrewise Anosov maps, if they are both Fibrewise Anosov maps, they have the same conjugacy and theorem applies.
Yeah.
Oh,
If on the basis is the same dimension.
yeah.
Other questions? Indeed, I have one. Here you use that your bundle is a principal bundle, so that you, at least at the linear part, it's clear. But for example, if you take the suspension of an Anosov map, then it's not a principal bundle, and it's clearly it has a meaning to be linear and hyperbolic in the fibers. So the same question has a meaning without principal bundle. And do you think you can linearize without this condition?
Yeah, I didn't think about it. I know I'm aware of that question, like I said here. But Newman-full fibers are not principal, right? But in like steps, it's hidden there. Many steps I use there is only translation. Yeah. So it's a nice question to think, I guess.
If no other question, so it's on Danyu again.